Hi everyone, thanks so much for watching and welcome back to Mostly Math for the thrilling conclusion to the two-part series about the generalization of the Schwarzschild solution to prove Birkoff's theorem. Now, as I explained last time, we're not going to actually prove the theorem, but we are going to do most of the tedious work that involves calculating the Ricci tensor components R, mu, nu, which we need the Christoffel symbols we calculated last time. You'll notice the new ones are the ones that have the time derivatives, this one, and this one. And I have included a list of the old ones. There are a few that are missing. These ones are not needed in the derivation. So let's just get started. Let's go ahead and calculate the one new component of the Ricci tensor when we let A and B go from R to, depending on both R and T, then we get the following new component. We obtain the component RTR, which, if we write out, it's going to be d sigma gamma sigma TR plus sigma kappa sigma kappa TR minus rth derivative sigma T sigma plus sigma kappa R kappa T sigma. Now, this is just the general definition of the Ricci tensor, where if I let T and R go to mu and nu, it's exactly the same. I just wanted to save the step of writing it since it is a long expression, and I'm going to make sure that I get it right. It's very important. All right, looks good so far. So the strategy that we're going to do is we're going to look at kappa and see what values correspond to the Christoffel symbols up there. We can easily see that kappa can only be equal to T and R, since there are T's basically in all of the gammas here, or R's alone. And if you want to have a T and an R, you need to have kappa be equal to T and R. So, for example, we have TTR up there, but we don't have TT. Well, we don't have a phi TR, for example. So this term doesn't make sense. That's just a brief guess as to why we would think it's true. To see that, you really have to just start plugging in values of kappa. So we'll do that now, and let's plug in some kappas. We are going to have d sigma TR plus sigma T sigma. See, we put in a T for kappa here. And again, this gives us another term with kappa being equal to R. Then we have similar terms over here. dr sigma T sigma plus sigma TR TT sigma plus gamma sigma RR RT sigma. Let's make sure I did that right. Should be the same kind of crap up here, but with kappa equal to T and R respectively. This term is the same. We have a sigma T sigma TTR, same thing with kappa being replaced by R. Here, this term is the same. Now we're going to have kappa being replaced by T. Good. And now by R. I think this is right. Let's proceed. Now it gets tedious. Basically, we just have to look at which values of sigma will give us non-zero answers. And when we do this, we see that sigma has to equal to T and R here. And the same thing here. But this one is different. It actually has all of them, since we have the theta and phi terms, like theta r theta and phi r phi as well, from these terms. So sigma is actually equal to everything here. And if we go over here, we find that sigma has to be equal to T and R again, everywhere else. Pretty sure, but let me just check that. Yep. Let's assume that's correct. Now comes the particularly tedious part of just plugging in all the letters for all this and seeing what comes out. So the first term we have time derivative of TTR plus the R derivative of RTR. Now we're on this term now, plus TTT. Oh, there's a couple terms here. TTT plus RTR times TTR. Last term for the top line. We're going to have a bunch of terms. TRT plus RRR plus theta R theta plus phi R phi, all multiplying RTR. And now we're going to subtract off a bunch of terms. Minus. What are we subtracting? Well, we have the rth derivative of TTT plus RTR. That's the first term. Plus TTR. TTT, that sigma equals T, plus RTR, TTR, sigma equals R, of course. Last term now, we're going to have TRR, RTT, plus sigma equals R, RRR, RTR. So you can see what I'm talking about by this being very tedious. It is very tedious. But if I've done this correctly, we can see that a bunch of terms will cancel. So let's see if I did it right. This term should cancel. We have the rth derivative of RTR, which thankfully it does cancel with this term here. Let's look at these bad boys here. TTT, TTR. Is that down here? Yes, it is. It's actually right here. Let's look at RTR, TTR. Well, it's actually right below it, which is nice. So far, so good. Now, TRT times RTR. Where's that one? I thought that one was supposed to cancel. Let's check it out. Nope, that one's not supposed to cancel. But this one is RRR times RTR. Yep, thankfully that one cancels. And let's see what's left here. Those are there. Good. And we are now going to show that these other derivative terms cancel as well. They don't outright cancel, but just watch what I'm going to do. Okay, so we have the time derivative of gamma TTR, which is just the time derivative. If we look up TTR up here, it's going to be a prime over 2a. Using the product rule, just going to be a prime dot times a minus a prime a dot over 2a. So that's just low d high minus high d low over across the bridge over g squared or something. However you remember it. This is suspiciously the same as the rth derivative of a dot over 2a, which is actually another one of the Christoffel symbols up there. A dot over 2a is gamma t t t. So the symbols aren't equal, but the derivatives are. So we can cancel them. And we're only left with a couple terms, which is fantastic. Okay. Let's just write down the terms that we have left. Well, we have t RT. Where is that? A prime over 2a. Plus these two terms. If I add 1 over r plus 1 over r, it's 2 over r. And now I have to multiply that by RTR, which is b dot over 2b. And now I have to subtract off the solitary term on the bottom. That is TRR times RTT. And miraculously, we see that this crap here is the same as the first term, so it cancels, leaving us with a surprisingly simple result, b dot over rb. This is our final answer here. We did all of this work just to show that our new Christoffel symbol, RTR, that's what we're calculating, it's the only new one, is just equal to one of the new derivatives divided by the radial component times the new function itself. And it should be noted, when you modify a and b to be time dependent, you get a few extra terms in the other ordinary Ricci tensor components. So those are the diagonal elements, our TT, our RR, our theta theta, and our phi phi. Obtain additional terms which, like the new component here, are proportional to a dot and b dot. And to find out what the terms are, you'd have to actually calculate the old Ricci tensor components using this form here. You would get to this step and you would show that there are more t and r terms basically. And you can certainly do that if you want. If you follow this derivation, I'm sure that you can derive the original Schwarzschild solution symbols, and you can use this in Birkoff's theorem by setting RTR equal to 0 to immediately show that b dot has to be 0, which is useful for the rest of the derivation. If you enjoyed this, want to see more, please feel free to like, subscribe. I'll see you next time. Thanks so much for watching my channel.